Hello everyone, I'm Brandon Guevara and I'm the team lead of Rails. Allow me to introduce the team for you. This is Raymond Ollinger and he is our hardware lead. The guy behind the camera, Matt McAfee, is our software lead. So before I get into the details of our role in this project, let me talk a little bit about the project as a whole. Near the end of 2008, a fatal train collision in California had occurred that has sparked a lot of controversy, questioning the safety of train transportation. This led to the adoption of the Rail Safety Improvement Act of 2008 that included the safety system known as positive train control. Let me give you a brief description of how positive train control works. The idea is a central base station will keep tabs of every train running on schedule and make sure that each train is not in danger of causing an accident due to high speeds or unauthorized entry into a section of track. If it detects such a possibility, it will automatically apply the brakes inside the train, bringing it to a stop. This safety system only interacts with the brakes, so it does not require to speed up the train. Now, after hearing about the safety system, a few teachers here at UAH decided they wanted to attempt to model such a system using a model railroad setup. They have been developing this model for the past couple years. Currently, the setup utilizes a model railroad system standard called DCC. The idea with this system is that specially made trains will pick up these pulse signals distributed on the rails that have encoded messages that control each train's movement. With this standard, it's possible to independently control each train. This may have been enough to model positive train control, however a problem was soon discovered. Looking underneath the current setup, you can see that there is a lot of circuitry and wires hooked up. When increasing the complexity and length of the track, it was soon realized that power on the rails was dissipating to a point where it was not giving enough power to each train. So it was necessary to divide up the track into sections and have all this circuitry used to make sure each divided section of track is providing enough power. However, this does not solve the problem. If we want to make an even more elaborate railroad setup, we would have to add more of this circuitry to prevent power dissipation. Due to this limitation, it was decided that our sponsors would like to begin shifting away from the DCC standard and possibly away from using the rails to power the trains entirely. So that's where we come in. Our part in this project is to take a regular DC model train and have them harvest power from the rails without having to decode a DCC pulse signal. We're still taking power from the rails since there is currently a student-developed safety system that is tied to the current DCC setup. These trains will be remotely operated from a computer application that we also created in order to communicate with each train. So here is an overview of our hardware design. First, here is our rectifier circuit. We have wires coming from the wheels that are connected to the inputs of each bridge rectifier. We then have this capacitor to smooth out the rectified signal from the bridge rectifier to get clean DC power. We then use this power to operate the Arduino, the XP radio, and the L298N motor driver directly. Arduino Micro is our main control system for our design. The motor driver will modify the DC signal to a suitable pulse width modulated signal specified by the Arduino that will power the motor directly. The Arduino controls 3 pins on this unit to determine speed and direction of the motor. For our project, it was requested that we also have a way to track the position of each train. So we have 2 position sensors, the optical tie counter and the RFID tag reader. The optical tie counter is essentially a line reader which is used to signal to us whenever the train has passed over a railroad tie. The RFID tag reader will output the unique address of any RFID tag. Throughout this model setup, there are multiple RFID tags glued onto certain parts of the track that act as landmarks for us to figure out what part of the track a train has entered. With these 2 sensors, it is possible to keep track of each train as they move. For now, we are only able to send out position data, but not translate them to positions on a virtual map of the track. This will need to be further evaluated by future teams. The XP radio will receive commands from our application as well as send out position data taken from the sensors. The Arduino handles what to send out from the sensors and how to interpret the command it receives. With this, we have our full hardware design. So let me briefly show off our software application that will be used to communicate with this hardware. Here is our software application. At the top right, we have a list of all the trains currently hooked up with our hardware. At the bottom right is our controls for adjusting the direction and speed for a selected train, which we select from the control at the top right. To the left of these controls is the text area that will output any feedback from our application as well as position data received from a train. At the top left under the File button, is a button that will pop up a window to set the connection to an XB radio connected by USB on this computer. And in the center of all of this is the virtual map of the track these trains will be running on. And that is our software application.